We're now going to look at a couple of practical planners in operation. You'll find some excellent online resources for some of the well-known planners listed in our table. The course readings have also been designed to introduce some of these, and we've provided screen captures of a number of our own Edinburgh planners in operation. Nonlin was created in the mid-1970s and, as mentioned earlier, was applied in a project using a mixture of AI and operations research (OR) methods to create project plans for electricity turbine overhaul. It allowed for user-driven modifications to the plans as maintenance inspections took place and plans had to be updated. Nonlin brought together a range of AI planning techniques which were novel at the time. In this slide, I'm using the terminology now commonly applied to these techniques. Nonlin was a hierarchical task network planner. It could generate plans in which the activities were not fully ordered. It had been common up until that time for AI planners to generate plans which were fully linear in order. Nonlin searches in a space of plan descriptions rather than in the application state space, a subject which we're going to cover in a later module. Nonlin uses the goal structure of the plan in considering the different alternatives, so it always looks at different approaches based on that plan rationale. Nonlin has a mechanism for answering the question of whether a proposition has a certain truth value at a certain point in the plan. We call that the QA module, question answering module. It's more often nowadays called the modal truth criterion. It used condition types to limit search. It allowed for multiple contributors to condition achievement in order to achieve plan robustness. It included compute conditions for links to external databases and systems because it was built as a practical planning system. These are similar to attached procedures in some other planners. And as mentioned earlier, it was a mixture of AI and operational research methods, so OR algorithms were used for time and resource constrained reasoning. Nonlin has been used as the basis for textbook descriptions of hierarchical task network planning. Oplan followed on from Nonlin and used some of the same techniques. It included domain knowledge elicitation and modelling tools and supported a rich plan representation. It also was a hierarchical task network planner and had detailed constraint management. It allowed for plugin constraint managers so that that aspect could be extended. Goal structure based plan monitoring during execution was supported, and it supported dynamic domains in which new objectives or tasks could arise while planning and execution was taking place. Plan repair, when time was available or when the situation demanded rapid response, was supported. Interfaces for users with different roles were provided in order that several different users could be refining the plan simultaneously and sharing information about the plan between them. An explicit management of the planning and execution workflow was supported, so the planner itself could be used in these aspects. Here is a simple example of Oplan acting as a Unix systems administrator's aid. The aim is to create a shell script that reliably removes a volume group. This is an application which a lot of people have found difficult and can lead to loss of files. Once the current mapping between logical volumes and physical volumes are given by the drop-down numeric boxes, you can just hit the plan button and the planner goes off and produces the plan, and it prints it out as the script ready to cut and paste and use. Here's a more comprehensive example of Oplan running on a military operations in urban terrain, where task description, planning and execution workflow are all able to be supported with multiple users acting over the internet and all sharing a common plan. So typically there would be a task assigner who would set up the problem. He would go in and define this with this simple web form with drop-down lists of the kind of tasks that can be carried out. And then a planner can be called to generate specific options and make suggestions of how to respond to the particular emergency, the particular disaster that's occurring. And the idea is that between the planner and the task assigner, they can talk and look at these options, refine them, throw away some, replan when things are being added, and so on. And all this is occurring through these user interfaces talking to the planner behind the scenes. Oplan was used as the basis for Optimum AIV, a planner for assembly, integration and verification of the payload bay of Europe's Ariane rocket launcher. It was originally designed as Plan ERS-1 for assembly, integration and test of the European Space Agency's ERS-1 spacecraft, shown here on the left. Optimum AIV also used a rich plan representation, hierarchical task network planning, detail constraint management. Plan and user rationale were recorded. It could handle issues arising during plan execution and deal with these through plan repair using test failure recovery plans. It was integrated with European Space Agency's Artemis project management system. Let me draw your attention to a number of features which are typical of practical AI planners. Often these are based on hierarchical task network planning at an outer layer. They often also allow for partial order of the resulting plans rather than insisting the plans are fully ordered. They often include a rich domain model. They can manage many types of constraints and include links to simulations and analyses to refine and restrict the plans. These planners often allow for integration with other systems, user interfaces, databases, spreadsheets, project management, corporate systems of various kinds. This is very typical of practical planners, and often much of the effort that goes into a practical planning application can go into this kind of integration.